In our last video, we looked at factoring 240 and at factoring 241. And we skirted around or just started to introduce these two new words, prime number and prime factorization of a number. So a prime number is any whole number with exactly two factors. One and itself. The prime factorization of a number is a product of prime numbers equal to the given number. Okay, so let's think about prime numbers. We looked at 2. If I try to write 2 as a product, the only way I can do that is 2 times 1. If I look at 6, I can do 6 times 1. I can write a product 1 times 6, but I have another choice here, 2 times 3. So 6 is not a prime number, it's a composite number. A composite just means not prime. It's composed of other smaller pieces. Whereas 2 is a prime number. In fact, it's the smallest prime number. If I try to use 1, if I'm looking at whole numbers, and with factoring we're only looking at whole numbers, I have to do 1 times 1 to get 1. So 1 does not have exactly 2 factors. It has exactly 1 factor. 1 is itself. So 1 is not a prime number. 6 is not a prime number. But 2 is a prime number. So for any prime number, the prime factorization is a bit of a joke, right? A product of prime numbers equal to the given number. So if I'm trying to write, say, 7 as a product of prime numbers, I could say 7 times 1, but 1 isn't a prime number. So technically, the prime factorization of 7 is 7. So it's kind of, but if we have something smaller, such as 6, we can say the prime factorization of 6 is 2 times 3. The prime factorization of 240 is 2 times 2 times 2 times 2 times 3 times 5. All of these. If we look at 241, it's actually a prime number. We'll see if there's a way to prove that easily without having to check. 2, no, 3, no, 4, no, 5, no, 6, no. It could take us a long time to try all the numbers to find out that there are none here. But if we go to 242, just a little bit higher, let's figure that out. So 242, right away, I hope you're noticing it ends with a 2, so it's even. It's going to be 2 times something to get 242. If we don't recognize it from anywhere else, I could have started with that. In fact, for 240, I could have started with 240 is 2 times 120. That's what I used for my list here. I didn't do that though, because first, this is more obvious. Anytime it ends in a 0, boom, I'm going to go straight to 10. If it ends with 2 zeros, I'm going to go straight to 100, right? That's almost always going to be the easiest path. The other advantage to this particular starting point is these are both somewhat middle-sized numbers. Factoring 24 is fairly easy. I've memorized that. It shows up on my times table. 120, that's still a 3-digit number. That's kind of big. So now I have to think, okay, well, 120, well, I can use the same technique as before. 10 times 12, now I've got two pretty small numbers. Or I could say, well, that's even again. Half of 120 is 60, and go on from there. The great thing about prime factorization is whatever route you take to get there, it's going to be the same. Because multiplication is associative and commutative. I'm multiplying these numbers. It doesn't matter what order I do it in. I could do the 5 times 3 to get 15, 15 times 2 to get 30, 60, 120, 240. Or I could do 3 times 2 is 6, and 6 times 2 is 12, and 12 times 5 is 60, and 2 times 2 is 4, and 60 times 4 is 240. There's lots of ways we can arrange these, but so long as we're only using each of these factors once, it'll work out. All right, so let's get back to 242. So half of 2 is 1, half of 4 is 2, half of 2 is 1. All right, it doesn't end in a 0. I couldn't jump straight to something times 10. 2 is the only number that showed up to me. So 2 is a prime number. Nothing I can do there. 121 is an odd number. It ends with a 1, so I'm not going to bother. 121 divided by 2. I know that's a dead end. For 3, let's see. 1 plus 2 is 3, plus 1 is 4. Or 1 plus 1 is 2. 2 and 2 is 4. 3 doesn't go evenly into 4, so 3 won't go evenly into 121. So 3's worthless. 4. I'm not going to try 4. If 4 worked, then 2 would have worked. So if some prime number doesn't work, like 2, then no multiple of that prime number is going to work. If there's no 2 here, then 4 can't be there either. Right? So if there's nothing obvious, if we're just trying to guess what might work, we really only have to check the prime factors, potential prime factors. So we're not bothering with 4. 5 doesn't end in a 5 or 0. That's out the window. 6. Now, if 2 didn't work, I'm not going to have 2 times 3 to get 6. So 6 I don't even have to think about. 7. 7 goes into 12. 7 doesn't go evenly into 51. Right? I'm showing you the shortcuts now. I don't care how many times 7 gets close to 51. I don't care what the remainder is. I care that there is a remainder. I can't do 7 times a whole number and get 51. So give up with 7. 8, no, 8 would have required 2. 9, no, 9 would have required 2. 10, no, not a prime, right? Would have required 2. 11, hopefully some of you already knew where this was going. 11 goes into 12 one time. Bring down the other one. Bring down the other one. 11 goes into 11 one time. 121 is actually 11 times 11. So the prime factorization of 242 is 2 times 11 times 11. All right. So for each whole number, it either is a prime number, or it doesn't really have a prime factorization, it just is, or it can be written as a product of primes, that is its prime factorization. And knowing that lets us very easily and quickly discover the greatest common factor of two numbers, and eventually the least common multiple of two numbers. We're going to use the prime factorization for both of those. Right now, we're just going to look at GCF, greatest common factor. Right? I'm not writing a definition for this because it's self-explanatory. If we know what a factor is, then we know what a common factor is. If I'm looking at 60 and 50, I can think of the factors of 60 and the factors of 50 and see what they have in common. So 60, there is 2 times 30. 30 is 3, let's do 5 times 6. 6 is 2 times 3. So that 5 is there. That 2 is there. So if I put it in order, 2 times 2 times 3 times 5. 50. That's 5 times 10. 10, that's 2 times 5. So if I put that in order, 2 times 5 times 5. So I'm using the prime factorization. I'm doing everything right. Here there's a 5 in common. Here there's a 2 in common. So they have 2 common factors, 2 and 5, right? There's a third common factor here. Because 2 and 5 together make 10, right? The most obvious common factor. Now, the greatest common factor is sometimes the one that's most obvious to us. In this case, the GCF is very easy to spot. But much of the time, it's not the first factor that comes to mind. Or maybe for some numbers, none of the factors come easily to mind. So we need some way to look at all of those potential common factors. So a factor is a number that's going to go evenly into my number. The factors of 50 are 2 and 5, and 2 times 5, which is 10, and 5 times 5, which is 25, and 50 itself, 1. Those are all the factors here. Listing all the factors of 60 is going to take me a while. Let's see, make this a little skinnier here. Well, I can do 1 times 60, of course. 2 times 30 is what I used. But if I started with 6 times 10, I don't see 2 times 30. I don't want to have to start from scratch again. Remember, we're starting here. So here's 2. So this other number, this product, has to be a different factor of 60. 2 times 3 is 6. 6 times 5 is 30. There's 30. Well, what's the next smallest number here after 2? I have a 3. So if I lump everything else, the rest of this times the 3 is going to give me 60. So 2 times 2 is 4. 4 times 5 is 20. So there's 3 times 20. All right, the next smallest number after 3 is 4. I can get 4. 2 times 2 is 4. So that leaves 3 times 5 is 15. Okay, here's 5. 5 times the rest of this. 4 times 3 is 12. 5 times 12. Okay, 6. 2 times 3 is 6. That leaves outer ones. 2 times 5 is 10. 7. There's no way to get 7 here. 8. I need 4 times 2 to get 8. I don't have a third 2 here. There's no way to get 8 for these pieces. 9. No, I need a 3 and a 3. 10. Well, I have a 10, but I already got 10. If I'm going to use 2 and 5 to get 10, That means I had to use 2 and 3 to get the other factor, right? By writing it in this order, with each small number being multiplied by the large number, as I go up, once I kind of hit this number, I'm going to start going back down this side. So once you've gotten halfway, how do you know you're halfway? Well, you know if you go any farther, you start to repeat what you had on the other side. Then you know you've gone halfway. Then you've exhausted it. So all the factors of 60 are right here. But if all I want is the greatest common factor, I don't need this list. Right? If all I want is the greatest common factor, I just need to look at the common factors. What factors do they have in common? They have a 2 in common and a 5 in common. So the only way to get any other common factors is some combination of these. What's the largest number I can get by combining 2 and 5 with multiplication? 10. And that's how we get GCF. So let's try to write that in words. To find the greatest common factor of two numbers, find all of their common prime factors then multiply. Now I do want to show you a shortcut to that because I've had students use this as the only way, and they're often shortcuts. So let's think of, instead of 60 and 50, let's try 240 and 220. All right. Now, we already know the prime factorization of 240, but let's say we don't, right? Do you remember how long that took us to get? That was a long list. 220, maybe not quite as many factors. But what do we notice right away? They both end with a 0. 24 times 10 gets me 240. Here, 22 times 10 gets me 220. They already have that as a common factor. Now, 10's fairly easy, 2 times 5. So if I get all of their prime factors, those are going to show up. And what's going to show up is that they have that 2 in common and the 5 in common. So they have that 10 in common. We are already much of the way there without going down to the nitty-gritty. So if you can spy a common factor right away, do that. If you have done so, or if you can't do that, then we keep on going with what we do have. So 24, I've got a lot of choices here. 2 times 12, 4 times 6, 3 times 8. 22, I only have one choice. 22 is 2 times 11. Well, 11 is not a factor of 24, but 2 is a factor of 24. My goal is to find their common factors. I found 10 as a common factor. Now I've got this other 2 as a common factor. What's left? 11. Its only prime factor is itself, 11. 12, it's got a bunch of prime factors, none of which are 11. So even if I kept on going, 11's not going to show up. My prime factors are 2 and the prime factors of 10. So I'll just leave those together as 10. 2 times 10 is 20. The GCF of 240, that's an O, of 240 and 220 is 20. See how we did that? We start factoring. If we see common factors, we're going to use that. If we get other factors along the way, we'll put those in. The fact that 2 already was a factor of 10 doesn't hide the fact that there's another 2 that they have in common. Now, these remaining numbers are also going to be important. This 11 matters. We want to not just see that 220 is 20 times something, but we need to recognize that it's 20 times, in this case, 11. And 240 is 20 times, in this case, 12. And the GCF here is 20. But to find the LCM, to actually factor polynomials, those other numbers are going to be important. So let's just do this one example. Let's say I asked you to factor the polynomial 240xy minus 220xp. I'm not sure I'm putting parentheses on there. 220xp. All right. Now, I know 240 is 20 times 12. xy after that means times x and times y. 220, I've already worked out that that's 20 times 11 times x times p. So what factors do they have in common? Running out of colors here. They have a 20 in common. I can factor that out. They also have an x in common. This term is 20 times x times 12 times y. This term is 20 times x. And then I can multiply that 20 times x times 11 times p. And then since this minus was in front, I need to keep that minus there to show that it's technically 20 times negative 11. That negative is staying with the 11, right? When we're factoring, I need to know not just what the greatest common factor is of those two coefficients. I also need to know, once I factor that out, what's remaining here. There are lots of techniques of finding the GCF that don't reveal this other number. My technique makes it pretty clear what that remaining portion is, and that's useful both in this context and in the context of fractions, which is where we're going to turn to next.